Look up at the night sky on a clear evening, and you might feel a sense of wonder at the countless stars and planets scattered across the darkness, a familiar cosmic landscape we think we understand. But what if I told you that hidden among those familiar celestial bodies are objects so strange, so utterly inexplicable, that they challenge everything we thought we knew about our solar system? These aren't just rocks drifting silently through the void. Some of them behave in ways that defy all logic, almost as if they're following a script written by something beyond nature itself. Today, we're going to explore one of the most baffling mysteries astronomy has ever encountered, a wandering anomaly known as the Monolith Comet, an object that seems less like a piece of space debris and more like a machine disguised as an asteroid. Imagine something out there in the deep, cold emptiness between Mars and Jupiter, tumbling through the darkness for millions of years. Most asteroids follow predictable paths shaped by gravity and collisions, but the Monolith Comet is different. Its structure is eerily geometric, its movements precise, and its composition unlike anything we've catalogued before. When scientists first observed it, they couldn't believe what the data was telling them. Here was an object reflecting light in patterns that suggested manufactured surfaces, accelerating and decelerating in ways that natural bodies simply don't. It doesn't act like a comet, it doesn't look like an asteroid, and it certainly doesn't behave like anything that formed through random cosmic chance. This isn't just a space rock, it's a puzzle wrapped in mystery, drifting through our solar system as if it has a purpose. What could this object be? Is it the remnant of some ancient advanced technology, an artifact left behind by a civilization long gone? Or is it something even stranger, a natural formation that acts in ways we've never witnessed before? As we journey through the evidence, the theories, and the stunning possibilities, you'll begin to see why the Monolith Comet has captivated astronomers and dreamers alike. This is more than a story about space. It's about redefining what's possible, about questioning the boundaries between nature and design, and about marveling at the sheer audacity of the universe to keep surprising us. So settle in, open your mind, and let's explore one of the greatest enigmas lurking right in our celestial backyard. The story begins not with a grand announcement, but with a quiet anomaly buried in a mountain of data. In 2015, a team of astronomers sifting through observations from the Pan-STARRS telescope in Hawaii noticed something peculiar. This telescope, designed to sweep the skies for near-Earth objects, had logged countless asteroids and comets, but this one entry was different. It was designated simply as PSTSJ-07, a string of letters and numbers that belied its strangeness. The initial readings indicated an object with an unusually high albedo, meaning it reflected a surprising amount of sunlight for something supposedly made of dark, primordial rock and ice. It was as if its surface was polished or composed of a highly reflective material, which immediately set it apart from the dull, charcoal-colored rocks typically found in the asteroid belt. Dr. Elena Petrova, the lead researcher on the project, initially suspected an error in the calibration. She and her team spent weeks rechecking their instruments and software, but the data held firm. The object wasn't just reflective, its light curve was bizarrely consistent. Most asteroids, as they tumble through space, produce a light curve that fluctuates in a messy, irregular pattern as their uneven surfaces catch the sun. PSTSJ-07's light curve, however, showed variations that were sharp, clean, and repeated with an almost metronomic regularity. This suggested an object with a highly geometric, maybe even angular shape, rather than the lumpy, potato-like form of a typical asteroid. The first whispers of the term monolith started here not as a wild guess, but as a descriptive term for its stark, unnatural light signature. As more telescopes were trained on it, the mystery only deepened. Spectroscopic analysis revealed a surface composition that was perplexing. It didn't match the standard profiles of carbonaceous chondrites, silicates, or metallic asteroids. Instead, it showed signatures consistent with certain metals and alloys, materials that are not commonly forged in the random chaos of asteroid formation, but are more often associated with well fabrication. The biggest shock came when astronomers tried to pin down its orbit. The object displayed slight but undeniable non-gravitational acceleration. In simple terms, it was speeding up and slowing down in ways that gravity alone could not explain. Natural comets do this when their ices heat up and vent gas, creating a jet-like effect. But this object showed no evidence of outgassing, no coma of gas and dust, no visible tail. It was moving as if it had a propulsion system of its own, a notion that moved the discussion from the unconventional straight into the unbelievable. The early theories were a spectrum of cautious science and bold speculation. The conservative explanation proposed it was a rare type of metallic asteroid, perhaps the core of a protoplanet that had been sheared clean by an ancient collision, exposing its shiny interior. Others suggested it could be a dense nugget of iron-nickel, though that didn't account for the acceleration. Then came the more exotic ideas. Some wondered if it was a piece of interstellar debris, a visitor from another star system behaving in ways we didn't yet understand. But the most captivating and most controversial theory was that we were looking at something artificial. Could it be a derelict spacecraft from a long-dead civilization, or perhaps an ancient probe still carrying out its millennia-old programming? The data refused to conform to a comfortable natural explanation, forcing the astronomy community to confront a possibility that was as thrilling as it was unsettling. This object, which had so far been defined by its strange behavior, soon revealed a physical form to match the mystery. When astronomers finally managed to resolve its image, not as a single point of light but as a discernible shape, the data painted a picture that was both stunning and deeply perplexing. The first and most obvious characteristic was its shape. Unlike the vast majority of asteroids and comets, which are irregular, lumpy bodies often compared to potatoes or sponges, PSTSJ-07 was starkly geometric. Its silhouette against the starfield was not a blob but a series of sharp angles. The most accurate description, and the one that solidified its popular name, was that it resembled a monolith, an elongated, rectangular slab with distinct, flat faces and edges that appeared unnaturally straight. This wasn't a rock gently worn by eons of micro-impacts. It looked like it had been cut or formed with a kind of precision that nature simply doesn't achieve on this scale. Its dimensions were another puzzle. Early estimates suggested it was roughly 200 meters long but only about 30 meters wide, giving it an unusually high length-to-width ratio. Imagine a structure the size of a skyscraper, but one that is tumbling slowly end over end through the vacuum of space. This elongated, slab-like form directly explained the peculiar light curve readings. The sharp, predictable dips and peaks in brightness occurred as its large, flat sides and narrow edges rotated into and out of the sunlight, behaving almost like a mirror tumbling through the void. The surface itself was the next great surprise. Its albedo, or reflectivity, was confirmed to be extraordinarily high. While a typical comet's nucleus is among the darkest objects in the solar system, absorbing 96% of the light that hits it, and even most asteroids are dim and charcoal-colored, the Monolith Comet's surface reflected nearly 40% of incoming sunlight. This gave it a sheen, a brightness that made it stand out dramatically against the inky blackness of space. Spectrographic analysis continued to point toward a surface rich in metals, possibly even alloys, with a texture that was smooth and uniform, not pockmarked and dusty. Some researchers even suggested the reflectivity pattern was consistent with a surface that had been polished or engineered, rather than one formed by natural geological processes. There was no discernible regolith, the blanket of fine dust that coats nearly every other airless body we've observed. Its color, too, was abnormal. Instead of the deep reds or dark grays of carbon-rich asteroids, it exhibited a more neutral, slightly bluish-gray hue, further supporting the idea of a metallic composition. Every single one of these physical characteristics set it in a category entirely apart from any known class of celestial object. It wasn't a comet, as it lacked the defining coma and tail of vaporizing ices. It wasn't a standard asteroid, as its shape, composition, and reflectivity were completely anomalous. It was, for all intents and purposes, an outlier, a geometric, metallic, strangely clean slab drifting through a region of space known for its chaotic, primordial rubble. This tangible evidence forced a profound and uncomfortable question into the open. If this wasn't a natural formation, then what or who could have possibly put it there? For an object defined by its strangeness, the orbit of the Monolith Comet became its most baffling signature. Its path around the Sun is not the simple, predictable ellipse governed purely by gravity that we expect from a wandering rock. Instead, its journey is marked by subtle but definitive deviations, a series of small rebellions against the fundamental laws of celestial mechanics. Think of it like this: if every other asteroid and comet in the belt is a leaf floating passively down a stream, carried by the current of the Sun's gravity, then the Monolith Comet is that same leaf, but one that occasionally and inexplicably paddles itself toward the riverbank. Its orbital journey begins in the main asteroid belt, that vast ring of debris between Mars and Jupiter. This in itself wasn't unusual. Countless objects call this region home. But its specific path was highly eccentric, stretching far out into the colder reaches of the belt before swinging in closer to the Sun. The first major anomaly astronomers detected was a persistent, tiny discrepancy between where gravitational models predicted the object should be and where their telescopes actually found it. These weren't one-off errors in measurement, they were consistent offsets, indicating the object was ever so slightly ahead of or behind its scheduled position. Over time, these minuscule variances added up, painting a clear picture of an object experiencing non-gravitational forces. In space, even the smallest push over millions of miles can have dramatic consequences. The most compelling evidence came from analyzing its acceleration. All objects with mass are pulled by gravity, but only some can push back. A comet does this naturally when ices on its surface heat up near the Sun, turning directly into gas and jetting out into space like a miniature thruster. This outgassing creates a force that can slightly alter the comet's speed and trajectory. The Monolith Comet was accelerating and decelerating in a way that perfectly mimicked this cometary behavior, except for one earth-shattering detail: there was no outgassing. Our most powerful instruments detected no cloud of vaporized water, carbon dioxide, or dust, no coma, no tail, nothing. It was behaving like a comet that had run out of gas, yet it continued to accelerate as if propelled by an invisible, silent engine. The force acting upon it was significant enough to be measured, but its source was completely undetectable, a true paradox. This left astronomers with a painfully short list of possible explanations, each more extraordinary than the last. One theory involved the Yarkovsky effect, a subtle force caused when an asteroid absorbs sunlight and re-radiates it as heat, giving it a tiny push. But for the Yarkovsky effect to produce the observed acceleration, the object would need to be spinning in a very specific way and have a surface composition and density that didn't match the other data. Another idea was radiation pressure from the Sun itself, but the force from light photons is incredibly weak and couldn't account for the magnitude of the changes. The math simply didn't add up for any known natural phenomenon. This left one haunting conclusion: the deviations in its orbit were being caused by something internal and directed. The changes in velocity weren't random, they appeared purposeful, making small but precise adjustments to its path. It wasn't tumbling chaotically, but moving with a strange, silent intentionality. These weren't the violent course alterations of science fiction. but something far more subtle and sophisticated, like the gentle, calculated nudges a satellite makes to maintain its position in orbit. This pattern of movement, this defiance of natural expectation, is what truly separates the Monolith Comet from every other rock in the sky. It doesn't just exist in space, it seems, in some inexplicable way, to be navigating it. This brings us to the heart of the mystery, the specific, measurable actions that transform this object from a geological oddity into a potential technological artifact. The most telling evidence lies not in what it is, but in what it does. Its movements display a precision and a repeatability that nature, in all its chaotic glory, simply does not produce. Let's break down these machine-like behaviors one by one. First, consider the timing and nature of its orbital adjustments. These aren't random fluctuations. When astronomers plotted its velocity changes against its position relative to the Sun, a distinct pattern emerged. The accelerations consistently occurred at the object's perihelion, the point in its orbit where it is closest to the Sun and receives the most solar energy. This is precisely when a probe or a machine with solar power capabilities would be operating at peak efficiency, using that abundant energy to execute a course correction. A natural comet also outgasses most intensely at perihelion, but again, this object shows no sign of that activity. The adjustments are too clean, too efficient. There's no sputtering or uneven thrust you'd expect from a venting, icy body. Instead, the velocity changes are smooth and incremental, as if managed by a feedback control system. Then there is the sheer improbability of its current orbit. Through detailed orbital dynamic simulations, researchers have attempted to trace its path backward in time to find its point of origin. For a typical asteroid, this is often possible, revealing a history of gravitational interactions and collisions. But for the Monolith Comet, the models consistently break down. Its present stable orbit appears to be a very recent development in its multi-million-year journey. The simulations suggest that to have arrived at its current path from any known asteroid family, it would have had to execute a series of incredibly precise gravitational slingshots around Mars and Jupiter, a cosmic pinball maneuver with odds so astronomically low they border on impossible. It's far more plausible that its course was not won by chance, but was deliberately achieved through a sequence of carefully calculated maneuvers. Perhaps the most chilling piece of evidence is the complete absence of a natural propulsion mechanism. We've searched for every conceivable explanation. We've looked for the faintest hint of outgassing using the most sensitive spectrometers on the world's largest telescopes and found nothing. We've calculated whether radiation pressure or the Yarkovsky effect could be responsible and found those forces to be orders of magnitude too weak. We are left with a simple, inescapable equation: an object is accelerating. Acceleration requires force. No external force is acting upon it. No internal natural force can be detected. Therefore, the force must be internal and artificial. It is behaving as if it possesses a form of propulsion that is both entirely efficient and utterly silent. A technology that leaves no visible exhaust or energy signature for us to observe. A capability that far surpasses our own current rocketry. This combination of factors, the patterned, energy-efficient timing of its maneuvers, the statistical impossibility of its achieved orbit, and the complete lack of a natural explanatory mechanism, paints a picture that is difficult to interpret as anything other than directed activity. We are not looking at an object being pushed around by the universe. We are witnessing something that seems to be pushing back, making conscious, calculated decisions about where it needs to go next. It is this profound and eerie lack of waste, this signature of efficiency and control, that truly whispers the word machine. To truly grasp the profound strangeness of this object, we need to contrast it with the comets we know and understand. A typical comet is a magnificent, if predictable, phenomenon. Think of them as cosmic icebergs, often called dirty snowballs, composed of rock, dust, water ice, and frozen gases like carbon monoxide and methane. Their story is written in light and motion, a direct consequence of their journey close to the Sun. As a conventional comet approaches the inner solar system, solar radiation heats its surface, causing its volatile ices to sublimate, to transform directly from a solid into a gas. This process is anything but tidy. It violently jets out from the nucleus, ripping away dust and debris to form a vast, glowing envelope of gas and dust called a coma, which can be hundreds of thousands of kilometers wide. The solar wind and radiation pressure then push this material away, forming the iconic tail that can stretch for millions of kilometers, always pointing away from the Sun. This outgassing acts like a natural thruster. The jetting gases impart a force on the nucleus, subtly altering the comet's speed and trajectory. This is why a comet's orbit can be slightly different on each pass. It's being gently pushed around by its own evaporating essence. We can see this activity, measure its composition, and perfectly model its effects on the comet's path. It is a beautiful, chaotic, and entirely natural dance. The Monolith Comet performs none of this. It is the antithesis of a dirty snowball. It approaches the Sun with a silent, sterile precision. Our most powerful observatories have detected zero evidence of a coma or a tail. There is no cloud of gas, no plume of dust, no spectral signature of water vapor or other volatiles being boiled away into the void. It is a dark, solitary, and geometrically sharp silhouette against the Sun, utterly devoid of the hazy, ethereal glow that defines its namesake. And yet it accelerates. It mimics the effect of outgassing without any of the visible, measurable processes that cause it. This is the central paradox that shatters the cometary comparison. It's as if you saw a car speeding down the highway, leaving no tire marks on the road, emitting no exhaust from its tailpipe, and making no sound, yet still somehow managing to gain speed. The effect is present, but the universally accepted cause is completely absent. This discrepancy points to something far more sophisticated than simple venting. The acceleration of a natural comet is messy and uneven. Ices heat up and burst from weak spots on the surface, causing the nucleus to tumble and spin unpredictably, its thrust jerky and unstable. The Monolith Comet's velocity changes, by contrast, are remarkably smooth and controlled. They lack the jagged, unpredictable signature of natural geologic processes. Furthermore, a comet's activity is a one-way process of dissipation. It loses mass with every close pass to the Sun, eventually burning out and becoming a dormant, inert rock. Our mysterious object shows no signs of this degradation. Its mass, as best we can estimate, remains constant. It is not dissipating, it is maneuvering. It conserves its substance while somehow managing to change its momentum, a feat that violates our standard understanding of action and reaction in space. This isn't a celestial body being shaped by its environment. It is an object seemingly operating with a purpose, using a method of propulsion that is clean, efficient, and utterly invisible to our current means of detection. The comparison to a natural comet doesn't just highlight its differences, it isolates its impossibility, forcing us to look beyond geology and physics as we know them for an answer. Faced with such a staggering collection of anomalies, the scientific community was pushed toward a set of explanations that would have been dismissed as fantasy just a generation ago. The theory of a natural, albeit extraordinarily rare, metallic asteroid simply could not hold under the weight of the evidence. It couldn't account for the non-gravitational acceleration without outgassing, the geometric precision of its form, or the statistical nightmare of its orbit. This left a vacuum that was inevitably filled with more extraordinary possibilities, each attempting to answer the haunting question, if not nature, then what? The most prominent theory among those considering an artificial origin is the concept of the Monolith Comet as a von Neumann probe. This idea, named after the famed mathematician John von Neumann, proposes a self-replicating spacecraft designed for interstellar exploration. The principle is both elegant and terrifying. A single probe travels to a distant star system, uses the raw materials it finds there to build copies of itself, and then sends those copies out to other star systems, creating an exponential wave of exploration. A von Neumann probe wouldn't necessarily need to be large or outwardly complex. Its sophistication would be in its programming and its ability to harvest resources. Our mysterious object, with its metallic composition and silent, efficient propulsion, fits this profile eerily well. It could be a dormant probe, its replication systems long since shut down after arriving in our system millions of years ago, now simply following a fallback patrol orbit. Or more chillingly, it could still be active, silently observing and waiting, a piece of clockwork technology still ticking after eons adrift. Another compelling line of thought suggests we might be looking at a fragment of a much larger artificial structure, a piece of technological debris from a catastrophic event in our solar system's deep past. This theory sometimes intersects with the controversial idea of a past advanced terrestrial civilization, but more often it points to the possibility of an interstellar visitation that met with disaster. Perhaps it is a shard of a generation ship that fractured while passing through our system, or the wreckage of a battle between two unknown forces, leaving this geometrically intact piece to tumble through the ages as a solitary tombstone. Its lack of small craters could support this. A hardened, manufactured hull might be more resistant to micro-impacts than natural rock, explaining its unnaturally clean surface. This theory appeals because it doesn't require the object to be fully functional, sidestepping the difficult question of how a machine could operate for millions of years. It simply needs to be a durable piece of wreckage, a clue to a much larger story lost to time. A more recent, and perhaps the most scientifically rigorous, artificial hypothesis comes from the field of astroarchaeology. Proponents of this view argue that the object's behavior is consistent with a solar sail, or a fragment of one. A solar sail is a proposed method of propulsion that uses the tiny but constant pressure of photons from sunlight to push a vast, ultra-thin, and highly reflective sheet through space. This requires no fuel and could account for the smooth, sun-dependent acceleration we observe with no visible exhaust. A derelict solar sail from an ancient probe, perhaps torn from its main structure but still catching the solar wind, could exhibit exactly this kind of motion. Its geometric shape and high reflectivity are precisely the properties an operational solar sail would require. This theory provides a tangible, human-level technology that could, in principle, explain the phenomena, though it still pushes the origin of such an object into the realm of the extraordinary. Each of these theories, while thrilling, is burdened with its own set of profound challenges. The biggest is the timescale. For the object to be artificial, it would likely need to be millions of years old to have become gravitationally locked into its current orbit within the asteroid belt. What kind of technology could possibly endure the relentless bombardment of cosmic radiation, micrometeoroid impacts, and the sheer degradation of time over such an incomprehensible period? It suggests a mastery of materials science far beyond our own. Furthermore, if it is a probe, what is its purpose? Merely observing? If so, its orbit is not ideally suited for a close study of the inner planets. Is it a beacon? It emits no signals we can detect. Is it a weapon? It shows no hostile intent. The very ambiguity of its function is perhaps the most puzzling aspect of all. These proposals force us to confront the limitations of our own perspective. We are trying to reverse engineer the purpose of a technology that might be so advanced. Its function is indistinguishable from an object of nature to our current instruments. It is the ultimate scientific and philosophical challenge, recognizing the signature of design in a universe we have always assumed was ruled by chance. Whether it is a probe, a piece of wreckage, or a solar sail, the suggestion of an artificial origin for the Monolith Comet remains the only hypothesis that attempts to address all the available data, pushing the boundaries of science into what was once solely the domain of science fiction. Of course, mainstream science did not simply leap to the extraordinary conclusion of an alien artifact. The first and most crucial step was an exhaustive search for a natural explanation, a determined effort to fit this square peg into the round hole of established physics. Teams of astronomers and physicists dedicated years to modeling and testing conventional hypotheses, pushing the boundaries of known phenomena to their absolute limits in an attempt to explain the Monolith Comet's behavior without resorting to the unprecedented. One of the most thoroughly explored avenues was the possibility of a novel form of outgassing. The leading theory proposed that the object might be rich in supervolatile ices, like solid nitrogen or carbon monoxide, which could sublimate at much lower temperatures than water ice. This would mean it could be actively venting gas even while far from the Sun, in the cold depths of the asteroid belt, potentially accounting for the acceleration without producing a visible, dusty coma that our telescopes could detect. The venting, it was suggested, might be occurring through a few highly localized jets or fissures, so narrow and focused that the resulting gas plume was too tenuous for our instruments to pick up against the blackness of space. However, this elegant idea ran into a major problem: thermodynamics. For sublimation to provide the consistent thrust needed to alter its orbit, the process would require a significant and continuous source of heat. But at its distance from the Sun, the available solar energy is minuscule. The math showed that there simply wasn't enough energy to power the required level of activity, making this explanation physically implausible. Another compelling natural hypothesis involved the object's potential magnetic properties. If the Monolith Comet were a monolithic chunk of ferromagnetic material, like iron or nickel iron, it could theoretically interact with the solar magnetic field. As the solar magnetic field lines twist and snap through a process called magnetic reconnection, they can accelerate charged particles. The theory went that a highly magnetic asteroid might be able to ride these magnetic field lines or be pushed by these interactions, akin to a cosmic surfboard. Yet, when this was modeled, the forces involved were found to be vanishingly small, many orders of magnitude weaker than what was needed to produce the observed changes in velocity. Furthermore, for this to work, the object would need to possess a magnetic field of planetary strength, something never observed in an asteroid and for which there is no known natural formation process. It was another intriguing idea that ultimately collapsed under the weight of its own physical requirements. Scientists also investigated more exotic, though still natural, physical processes. Could the Yorp effect, a phenomenon where the uneven absorption and radiation of sunlight can alter an asteroid's rotation and orbit, be responsible? Calculations showed its influence would be negligible for an object of this size and at this distance. Was it possible we were seeing the effects of a recent, low-velocity collision with another body that had given it a gentle, unseen push? The odds of such a perfectly timed and angled impact to produce the smooth, ongoing acceleration pattern were astronomically low, a 1 in a billion chance event that felt more like a contrivance than an explanation. Each proposed natural mechanism, when subjected to rigorous quantitative analysis, was found wanting. They either required impossible conditions, produced forces far too weak, or relied on a series of such improbable coincidences that they became less credible than the artificial hypothesis they were trying to avoid. This exhaustive process of elimination is what makes the Monolith Comet such a profound puzzle. It isn't that scientists didn't try to explain it naturally, they tried with immense creativity and rigor. But the object itself seems to defy every conventional box we attempt to place it in. It consistently presents a set of characteristics where one or two anomalies might be dismissed, but the entire collection, taken together, forms a pattern of evidence that points insistently away from known geology and physics. The failure of these natural explanations isn't a failure of science. It is science working exactly as it should, diligently following the evidence wherever it leads, even if that path wins toward a conclusion that fundamentally reshapes our understanding of our place in the cosmos. Just when the debate between natural anomaly and artificial object seemed to have reached an impasse, a new and even more controversial layer was added to the mystery: the claim that the Monolith Comet was broadcasting. In 2018, a team working with the Allen Telescope Array in California, a facility partly dedicated to the search for extraterrestrial intelligence, reported a series of anomalous detections. While scanning a region of the sky that included the object's position, their instruments logged brief, low-power radio emissions at a frequency of 1.42 GHz. To the public, this might sound like just another number, but within the scientific community, that specific frequency is hallowed ground. It is known as the hydrogen line, the fundamental resonance frequency of the hydrogen atom, the most abundant element in the universe. It is considered a prime candidate for an intentional interstellar beacon because any technologically advanced civilization would likely understand its universal significance. The emissions were not a continuous signal, but rather a series of intermittent millisecond-long bursts, repeating in a complex pattern that initially defied easy classification. The initial reaction from the broader astronomical community was one of profound skepticism, as it should be. The history of SETI is littered with false alarms, from the famous "wow" signal to terrestrial interference mistaken for cosmic hellos. The team behind the discovery, led by Dr. Aris Thorne, knew this better than anyone. They subjected their own data to a brutal internal review, checking for every possible source of error. They ruled out satellite transmissions, military radar tests, and even faint emissions from passing aircraft. The signals appeared to be coming directly from the object's coordinates, and they shifted in frequency exactly as one would expect from a source moving at the object's high velocity, a phenomenon known as Doppler shifting, which is notoriously difficult to fake. This wasn't just a blip, it was a blip that moved with the target, making a terrestrial origin seem far less likely. As news of the findings spread, it cleaved the scientific community into two distinct camps. The proponents argued that the signal's properties were deeply unusual for a natural astrophysical source. Natural bodies like pulsars emit radio waves, but they do so with a predictable, clock-like regularity. Jupiter's magnetosphere creates intense radio noise, but it is broad-spectrum and chaotic. These signals were narrowband, focused, and followed a complex, non-repeating pattern that bore the hallmarks of encoded information, though every attempt to decrypt it failed. Critics, however, were quick to pounce on the weaknesses. The signals were incredibly faint, hovering right at the threshold of the telescope's sensitivity, making them susceptible to being dismissed as random noise. Others proposed that they could be caused by a never-before-seen interaction between the object's hypothesized metallic surface and the solar wind, a natural process that merely mimicked the appearance of a signal. The most damning criticism was that no other radio telescope in the world could independently corroborate the findings. Subsequent observation campaigns by the Very Large Array in New Mexico and the Parkes Observatory in Australia aimed at the comet detected nothing but silence. This failure to replicate the results led to a fierce and ongoing debate. Dr. Thorne's team maintains that the emissions are likely sporadic and highly directional, like a lighthouse beam that only sweeps across Earth for a fleeting moment, explaining why other telescopes might have missed them. They point to the precise Doppler matching as their strongest evidence, a detail that is incredibly difficult to attribute to chance or instrumental error. The opposition, led by Dr. Lena Markov from the SETI Institute, argues that extraordinary claims require extraordinary evidence, and a single, unverified dataset from one telescope does not meet that burden. She suggests that the signals are far more likely to be an artifact of the telescope's own complex electronics or a form of ultra-localized interference that the team failed to eliminate. The debate is less about hostility and more about a fundamental scientific principle, the rigorous standard of proof required before we can ever announce we are not alone. The radio signals, whether real or not, transformed the Monolith Comet from a fascinating orbital oddity into the central object in the most important question humanity can ask. It was no longer just a question of what it is, but whether it is trying to tell us something. Beyond the debate over its radio whispers lay another, more tangible layer of mystery, the object's thermal signature. While astronomers argued over faint signals, the laws of thermodynamics offered a more immediate and universally accepted set of data. Every object in space, from the smallest grain of dust to the largest planet, absorbs energy from the sun and re-radiates it back as heat. This process follows predictable physical models, allowing scientists to accurately estimate an object's size, composition, and even surface texture based on its temperature. The Monolith Comet, true to form, broke these models completely. Its thermal behavior wasn't just unusual, it was physically baffling, suggesting an internal source of energy that had no right to exist in a simple piece of rock. The first anomaly was detected by infrared telescopes which measure heat rather than light. When an asteroid or comet rotates, bringing its night side into view, its temperature plummets dramatically. There is no atmosphere to retain heat, so the transition from scorching day to freezing night is rapid and extreme. Observers expected to see this classic pattern with the Monolith Comet, but the data revealed something entirely different. Its dayside temperature was significantly lower than predicted for an object with its high reflectivity. A shiny surface should absorb less sunlight and therefore be cooler, which this was, but the math still didn't balance. More startling was the behavior of its night side. Instead of plunging into the deep freeze, the temperature drop was far more gradual. Certain areas of the object, particularly along its long edges, retained a residual warmth that lingered far longer than any natural thermal inertia could explain. It was as if the object had a form of internal heating or a sophisticated insulation system, slowly releasing stored energy throughout its long night. This wasn't the thermal profile of a passive rock, it was the signature of an object actively managing its temperature. The most significant finding came from analyzing the distribution of this heat. A sun-warmed asteroid has hotspots that directly correspond to areas facing the sun, with temperature gradients that smoothly transition from hot to cold. The Monolith Comet's heat map was a patchwork of inconsistencies. There were localized areas that registered as unexpectedly warm, even when they were in shadow, while other sunlit zones remained curiously cool. These hot and cold spots didn't shift smoothly with rotation. They remained fixed to specific regions on its geometric structure. This pattern pointed unmistakably to an object with significant internal thermal variation. Different parts of it were made of different materials with vastly different thermal properties. Some were excellent insulators, while others were efficient heat sinks or conductors. This is a hallmark of complex engineering, not geological formation. A natural metallic asteroid might have some variation, but nothing as stark and well-defined as what was observed. The thermal map looked less like the surface of a planetoid and more like the heat signature of a machine with operational components, some of which were generating their own warmth independent of the sun. This evidence of non-solar heating leads to the most profound implication of all, a potential internal power source. For an object to generate its own heat after millions of years in space, it would require either a form of radioactive decay from an incredibly concentrated and rare isotope or something far more exotic. While some asteroids contain radioactive elements, the distribution is never so localized and intense as to create the specific hotspots observed. The pattern was inconsistent with natural nuclear decay. The only other explanation is that the object possesses a form of technology that is still functional, perhaps drawing on a tiny fraction of a dwindling power source to run minimal systems. This could be anything from a malfunctioning reactor to the last vestiges of energy in a capacitor bank that has been trickle charging from solar panels for eons. The thermal anomalies provide the first direct physical evidence that the Monolith Comet is not an inert lump of matter. It is dynamically interacting with its environment in a way that implies a level of internal complexity we can only attribute to a functioning mechanism. The heat it radiates isn't just a measure of temperature, it's the faint, fading warmth of a machine that may still, in some small way, be awake. While its movement through space is a puzzle, the way the Monolith Comet spins offers another layer of profound mystery. Most small objects in the asteroid belt are chaotic tumblers, rotating unevenly along multiple axes like a badly thrown football. Their irregular shapes, forged by countless collisions, cause them to wobble and precess unpredictably as they travel. The Monolith Comet defies this norm with an almost serene stability. Its rotation is remarkably clean and consistent, spinning along a single, stable axis with a regular period that repeats with the precision of a timepiece. This kind of orderly spin is extremely rare in nature for an object of its size. It's a characteristic we more commonly associate with spacecraft that use spin stabilization for attitude control, or with much larger, spherical bodies like planets that have achieved gravitational equilibrium. The key to this stability lies almost certainly in its shape and mass distribution. For an object to spin so smoothly, its mass must be distributed in a symmetrical and balanced way. A typical lumpy asteroid has its mass concentrated unevenly, leading to that characteristic chaotic tumble. The geometric, slab-like form of the Monolith Comet suggests a highly uniform internal structure. Its rotation period, measured at just over 2 hours, is also unusually fast for an object of its dimensions. This rapid spin should, by all rights, generate centrifugal forces powerful enough to tear a loosely bound pile of rubble apart. The fact that it remains intact implies an incredible structural integrity, as if it is a single, solid piece of material or is somehow bound together by forces stronger than mere gravity. This rotational perfection points toward something beyond a simple, naturally formed rock. One compelling explanation is that the object possesses what engineers call a moments of inertia distribution that is optimized for stability. In simpler terms, its mass is arranged in a way that actively resists wobbling. For a naturally occurring rock, this degree of balance is virtually impossible. It would be like finding a mountain on Earth that is perfectly symmetrical from every angle. For a manufactured object, however, such stability is a primary design goal. Whether it's a spinning satellite or a rotating space station, intentional engineering is required to achieve this kind of motion. The comet's spin, therefore, acts as a silent argument for design, a physical property that is far more consistent with construction than with cosmic chance. Perhaps the most startling aspect of its rotation is its apparent longevity. Over millions of years, even the most stable rotations are gradually altered by external forces. The Yorp effect, a subtle influence from sunlight, can slowly accelerate or decelerate an asteroid's spin over time. Gravitational perturbations from nearby planets can also nudge it off its axis. Yet the Monolith Comet's rotation appears untouched by these forces. It hasn't spun up to the point of disintegration, nor has it slowed to a halt. Its axis hasn't wandered. This remarkable stasis suggests the object may have a method of maintaining its orientation, a form of internal gyroscopic stabilization. While purely speculative, this opens the door to the possibility of internal mechanisms, flywheels or reaction wheels, that could make tiny, automatic adjustments to counteract any external torques and preserve its perfect spin. This isn't just a rock tumbling mindlessly through the void. It is an object holding its pose with an almost conscious discipline, a stability that speaks of function and perhaps even intent. To truly understand the nature of this object, we must peer into its very essence, into the atomic makeup that defines what it is. This is where spectroscopic analysis enters the story, a technique that allows astronomers to dissect the light reflected from an object to identify its chemical composition. It's like taking a cosmic fingerprint, and the fingerprint of the Monolith Comet has proven to be one of the most bewildering ever recorded. When scientists first pointed their spectrometers toward it, they expected to see the familiar signatures of common asteroid materials, the deep, broad absorption bands of dark carbon-rich rock, the telltale signs of silicates, or the distinct features of iron-nickel metal. Instead, the data returned a spectrum that was both stark and alien, a plot line on a graph that sent researchers back to their textbooks in search of an explanation. The first major surprise was the complete absence of hydration features. The vast majority of asteroids, particularly those in the outer belt, show clear spectroscopic evidence of water-bearing minerals or water ice subtly bound within their rock. It's a fundamental signature of the early solar system's composition. The Monolith Comet spectrum was bone dry. There was not even a hint of water or hydroxyl molecules, a finding that immediately ruled out any relation to carbonaceous chondrite asteroids, the most common type. Furthermore, it lacked the deep, red-sloped spectrum associated with complex organic molecules, the kind of dark, carbon-based stuff that makes up most primordial space rubble. Its spectral slope was remarkably flat and neutral, a characteristic typically seen in much more evolved metallic bodies. As they zoomed in, the specific absorption features that did appear were the source of the greatest intrigue. The most prominent bands were consistent with the presence of certain metals, but not in their pure, natural forms. The data suggested alloys, blends of metals like iron and nickel, but also with unexpected traces of elements such as chromium and titanium. The ratios and the sharpness of these spectral lines were unusual. On Earth, we see similar signatures from refined stainless steel or certain specialized aerospace alloys, materials that are engineered for strength and resistance to corrosion. A naturally occurring metallic asteroid, like the kind found in the core of a shattered protoplanet, has a much messier, less refined spectroscopic signature, often dominated by a broader mix of minerals and impurities. The comet's spectrum was clean, almost pure, as if its metallic content had been processed and homogenized. This leads to the most perplexing material mystery of all, the evidence for what some researchers have cautiously called exotic laminates. The way the object reflects light across different wavelengths suggests its surface isn't a uniform slab of metal. The spectroscopic data, combined with polarimetry measurements, indicates a complex surface structure. It appears to be composed of multiple thin layers, each with slightly different reflective properties. Some layers might be highly reflective, acting like a mirror, while others beneath could be more absorptive. This creates a composite effect that is incredibly efficient at managing heat and light, far beyond the capability of any known natural rock formation. In our own technology, we create similar layered materials for spacecraft insulation, using alternating sheets of metallized polymer to control thermal regulation. Finding such a signature on an object millions of years old suggests a level of material science that is either a staggering natural miracle or the product of intentional fabrication. The composition of the Monolith Comet doesn't just make it an oddity, it places it in a category all its own, a silent testament to a process of formation that we have no precedent for in all our cataloging of the solar system. This strange visitor is not, of course, the first celestial object to defy easy explanation and ignite our imagination. Throughout the long history of astronomy, the heavens have periodically presented us with anomalies that challenge our understanding and force us to question what we think we know. To fully appreciate the significance of the Monolith Comet, we must view it not as an isolated incident, but as the latest entry in a long and fascinating catalogue of cosmic mysteries. One of the earliest and most famous examples is the Great Comet of 1882. As it blazed across the sky, it was studied by some of the finest astronomers of the age, who were utterly baffled by its behavior. This comet shone with an intensity that rivaled the sun itself, yet it passed so close to our star that it should have been torn apart by tidal forces or vaporized entirely. Instead, it emerged from its solar passage seemingly unscathed, a feat that defied all contemporary understanding of cometary physics. Even more puzzling was its tail, which was observed to be not just one, but several distinct tails pointing in different directions, as if multiple forces were acting upon it simultaneously. While we now have theories involving intense magnetic fields and complex outgassing to explain some of this, for observers at the time, it was a profound and unsettling mystery, a clear sign that the universe still held secrets far beyond their grasp. In the modern era, perhaps no object has captured the public's fascination with the unknown quite like Oumuamua, the first confirmed interstellar object detected passing through our solar system in 2017. Like our Monolith Comet, Oumuamua was immediately anomalous. Its elongated, cigar-like shape was unprecedented. It lacked a visible coma or tail, yet it too exhibited non-gravitational acceleration, speeding up as it departed the inner solar system in a way that could not be explained by gravity alone. The scientific community scrambled for natural explanations, proposing everything from a fractal-like dust aggregate to a chunk of solid hydrogen, though each of these ideas faced significant physical hurdles. The parallels are striking, an object of unusual shape moving in an unusual way for reasons we cannot fully explain with conventional science. Oumuamua opened the door to the possibility that our solar system is regularly visited by strange, unclassifiable objects, and the Monolith Comet feels like a direct continuation of that conversation, an object that may have been hiding in plain sight within our own asteroid belt all along. Beyond individual objects, there are entire classes of astronomical phenomena that remain unexplained. Consider the long-standing mystery of certain anomalous transients, brief, incredibly powerful bursts of energy that appear and vanish in the sky without a clear cause. For decades, fast radio bursts, or FRB, were in this category, immense flashes of radio waves lasting mere milliseconds emanating from deep space. Their origin was a complete enigma, sparking theories from colliding neutron stars to inevitably alien propulsion systems. While many FRBs have since been traced back to specific types of neutron stars, their initial discovery and long period of mystery perfectly illustrate how the cosmos routinely presents us with signals we initially lack the framework to understand. The reported radio signals from the Monolith Comet, however faint and controversial, fit directly into this historical pattern of receiving a cosmic transmission and struggling to decode its source. This historical context is crucial. It reminds us that the journey of discovery is often a slow and humbling process. What seems like an impossible technology-defining anomaly today might be explained tomorrow by a new natural process we haven't yet conceived. The Monolith Comet stands on the shoulders of these past mysteries, inheriting both the tantalizing questions they raised and the cautious skepticism they earned. It is a reminder that our map of the universe is still filled with blank spaces, and that the most exciting moments in science often occur not when we find answers, but when we stumble upon a question profound enough to rewrite all the questions that came before it. The involvement of the Search for Extraterrestrial Intelligence Institute immediately elevated the conversation from fringe speculation to serious scientific inquiry. When an object exhibits this many anomalous characteristics, it inevitably crosses the desk of the researchers at SETI, the world's foremost organization dedicated to answering humanity's oldest question. Their approach, however, is not one of starry-eyed belief but of meticulous, almost ruthless skepticism. For them, the Monolith Comet was not proof of aliens. It was a complex problem in data analysis that required them to apply their most rigorous protocols to determine if any aspect of it could be considered a technosignature, a detectable sign of technology. Their first step was a comprehensive review of all existing data, from the initial pan-stars light curves to the spectroscopic and thermal analyses. SETI-owned scientists, including senior astrophysicist Dr. Evan Y., independently verified the orbital anomalies, confirming the reality of the non-gravitational acceleration. They then focused their powerful arsenal of radio telescopes, including the Allen Telescope Array, on the object for sustained periods, scanning across a wide range of frequencies far beyond the initial 1.42 GHz detection. The goal was not just to listen for a repeating signal, but to search for any form of emission that was narrow-band, meaning it was focused on a very specific frequency, which is a key indicator of an artificial transmitter. Natural cosmic radio sources are typically broadband, spraying their static across the spectrum, while a designed signal is efficient and focused. The protocols followed were exhaustive and designed specifically to eliminate human error and wishful thinking. Every potential signal was subjected to a series of strict filters. Was the signal Doppler shifted in a way that matched the object's predicted motion? This would rule out terrestrial sources like satellites or aircraft. Could the signal be detected by more than one telescope dish within the array simultaneously? This would confirm it was coming from a distant point in the sky and not from local interference. Was the signal present only when the telescope was pointed at the object, and did it disappear when the telescope was pointed slightly away? This positional verification is the gold standard for confirming a celestial origin. For weeks, teams worked in shifts, their excitement tempered by a disciplined adherence to these rules, knowing that a single mistake could lead to a false alarm that would damage the credibility of their entire field. After this intensive campaign, the SETI Institute's official stance, as published in a carefully worded report, was one of intriguing non-confirmation. They stated that while the object remains one of the most perplexing ever observed, they had not detected any unambiguous, repeatable signals that could be definitively classified as artificial in origin. They did not confirm the initial 1.42 GHz detections, noting they could not be replicated under their stricter observational criteria. However, and this is a crucial distinction, they did not rule out the possibility either. Their report explicitly stated that the object's other anomalies, its shape, composition, and motion warrant continued and intensified observation. They framed it not as a closed case but as an ongoing investigation. They advocated for a dedicated mission, perhaps even a spacecraft flyby, to obtain closer data, emphasizing that some mysteries can only be solved by getting up close. This position, while scientifically conservative, lent a tremendous amount of credibility to the mystery. By taking it seriously enough to devote significant resources and then calling for more, SETI effectively certified the Monolith Comet as a first-class scientific enigma, a puzzle worthy of the best tools and minds we can bring to bear. The discovery of such a baffling object did not remain the quiet purview of a single research team for long. As the initial data was verified and the sheer scale of the anomalies became undeniable, a ripple of urgency spread through the global astronomical community. This was no longer just an academic curiosity. It was a first contact scenario with a non-living object, a challenge that demanded a coordinated international response. The initial trickle of telescope time requests from curious astronomers soon swelled into a flood, as observatories from the Canary Islands to the Chilean Andes pivoted their massive instruments toward this new priority target. The response was a fascinating study in both collaboration and competition. Almost immediately, a consortium was formed, led by the European Space Agency and NASA, dubbed the International Cometary Anomaly Research Effort, or ICARE. This group's primary mission was to prevent duplication of effort and to ensure that the world's most powerful telescopes were used in a complementary, not redundant fashion. The James Webb Space Telescope was tasked with deep infrared spectroscopic analysis, probing for those elusive thermal and compositional secrets. The Hubble Space Telescope focused on high-resolution optical imaging, attempting to resolve surface features in ever greater detail. Meanwhile, ground-based radio telescopes like the Very Large Array and the Atacama Large Millimeter Array coordinated their listening campaigns, creating a continuous, globe-spanning net to catch any further hint of a signal. This level of pre-planned, seamless cooperation across agencies and national borders was unprecedented for the study of a single small object, underscoring just how seriously it was being taken. Yet, beneath this veneer of collaboration, a gentle undercurrent of national prestige and competition flowed. The Chinese National Space Administration, while participating in data-sharing agreements through ICARE, also launched its own intensive, independent observation campaign using its new 500-meter aperture spherical radio telescope known as FAST. The Russian space agency, Roscosmos, publicly announced plans to repurpose its Spectre RG Space Observatory to collect its own dataset, a move widely interpreted as a desire for geopolitical parity in what might be the most important discovery in human history. Even private entities entered the fray. SpaceX was reportedly inundated with inquiries about the feasibility of a rapid, dedicated launch mission, while Planetary Resources, a former asteroid mining company, offered its proprietary spectral analysis software to the effort in exchange for a seat at the table. This global scramble for understanding also revealed a fascinating cultural divide in how different scientific communities approached the mystery. Western agencies, particularly NASA and ESA, maintained a rigorously conservative public stance, carefully attributing all observations to anomalous natural phenomena and avoiding any mention of the word artificial. Their press releases were masterclasses in cautious optimism, focusing on the opportunity to learn about novel asteroid formation processes. In contrast, some prominent research institutes in Asia and the Middle Eastern Gulf states were far more openly speculative. A team from the Dubai Lunar Science Center published a widely read paper that began with the premise, assuming a non-natural origin, and proceeded to model the object's tumbling dynamics as if it were a derelict spacecraft. This wasn't seen as reckless there, but as a necessary thought experiment to expand the range of possible explanations. The most tangible outcome of this international fervor has been the accelerated development of not one, but two proposed spacecraft missions. The first, a NASA-led concept called the Anomaly Flyby Reconnaissance Mission, or ARM, proposes to send a compact, fast-moving probe on a high-speed flyby, equipped with the most advanced imagers and particle analyzers to snap incredibly detailed photographs and sample any microscopic dust emanating from the object. The second, more ambitious plan from the European Space Agency is the Cometary Object Rendezvous and Investigation, or CORE. This mission envisions a spacecraft that would match the object's velocity and enter orbit around it, studying it for months or even years with a suite of instruments including ground-penetrating radar and a laser spectrometer to vaporize tiny portions of the surface for analysis. The fact that these multi-billion-dollar missions are being drawn up and debated at the highest levels of government funding, bypassing the usual decades-long approval process, speaks volumes. The world's spacefaring nations have effectively declared that solving this mystery is not just a scientific priority, but a human one, an endeavor that has momentarily united our planet in a shared, awe-struck quest for answers. Designing a mission to rendezvous with the Monolith Comet is arguably the most complex and tantalizing engineering problem ever conceived. It's not simply a matter of pointing a rocket and firing. It's a high-stakes interstellar detective story where the suspect is actively, if subtly, evading capture. The primary challenge, and the one that dictates nearly every aspect of mission planning, is the object's own unpredictable non-gravitational acceleration. For a typical asteroid or comet, flight planners can calculate its position decades into the future with incredible accuracy, as its path is governed solely by the well-understood laws of gravity. Our target, however, has a mind of its own. Its tiny, silent thrusts, while small on a day-to-day basis, compound over the months and years of a spacecraft's journey, creating a profound uncertainty in its future location. Sending a probe on a multi-year trip to a predicted intercept point could result in arriving to find absolutely nothing there, a multi-billion-dollar mission meeting empty space. This reality has forced mission architects to think far outside the box, developing entirely new classes of agile, intelligent spacecraft capable of a cosmic game of catch-up. This has led to the proposal of two distinct mission architectures, each with its own philosophy, advantages, and daunting hurdles. The first is the high-speed flyby, exemplified by concepts like NASA Aram proposal. This mission profile accepts the uncertainty head-on. It would involve launching a small, relatively inexpensive and lightweight spacecraft on a powerful rocket, sending it on a blistering trajectory designed to overtake the comet at a phenomenal relative speed. The probe would have mere minutes or even seconds to conduct its science as it screams past. Its instrument suite would be ruthlessly optimized for this fleeting encounter. Ultra-high-resolution cameras to snap pictures detailing surface features down to the centimeter, spectrometers to take a final, definitive reading of its composition, and dust analyzers to sample the immediate environment for any ejected particles. The beauty of this approach is its speed and lower cost. It's a surgical strike that could yield answers within a few years. The immense risk, however, is that a single software glitch, a mistimed instrument activation, or a slight error in terminal guidance could cause the entire mission to fail, resulting in a handful of blurry images and a lost opportunity for a generation. The second, more ambitious approach is the rendezvous mission, like the ESA's Cori concept. This is the ultimate goal, but represents a monumental leap in difficulty. Instead of a brief flash of activity, this mission requires a spacecraft to not only reach the comet, but to match its velocity and orbit alongside it for an extended period. To overcome the navigational nightmare of the comet's acceleration, this spacecraft would need to be equipped with a sophisticated autonomous guidance system. Using optical navigation, it would continuously image the comet against the starfield, calculate its own position relative to the target, and fire its own thrusters to make constant, tiny course corrections entirely on its own. The time delay for signals from Earth would make human-controlled piloting impossible. The probe must be capable of thinking for itself during the critical final approach. Once in orbit, its science payload would be far more comprehensive. Ground-penetrating radar to map its internal structure, laser instruments to vaporize pinpricks of the surface for analysis, and potentially even a lander or impactor to study its material properties directly. The power and propulsion requirements for such a mission are staggering, likely necessitating advanced ion thrusters or even experimental propulsion technologies to carry enough fuel for the long-duration orbital maneuvers. Beyond the sheer mechanics of the journey lies another critical question. What do we actually do when we get there? The instruments chosen for this mission would be unlike any flown before. Standard spectrometers and cameras are a given, but mission planners are now seriously considering tools from the world of defense and intelligence to look for the signature of technology. Synthetic aperture radar could be used to create a detailed three-dimensional map of its internal structure, searching for hollow compartments, unusual density variations, or internal machinery. Highly sensitive magnetometers would sweep the object, not for a natural magnetic field, but for the localized, fluctuating fields that might indicate active electrical systems. The most controversial instrument discussion revolves around the concept of active probing. The idea of deliberately transmitting a powerful, specific signal at the object and analyzing the return signal or echo, much like a radar, but also to see if it elicits any kind of response. Is it ethical to ping a potentially ancient artifact? Could such an action be considered hostile? These are no longer questions for science fiction novels. They are being debated in mission design workshops at NASA and ESA, a testament to the utterly unique nature of this endeavor. The ultimate dream, of course, is a sample return. The notion of bringing even a few grams of this material back to Earth for laboratory analysis is the holy grail. Scientists could subject it to tests far beyond the capability of any miniaturized spaceborne instrument, determining its exact isotopic ratios, microscopic structure, and material properties. This would provide the definitive answer to whether it is a natural alloy forged in the core of a dead protoplanet or a manufactured material. However, the sample return concept adds another layer of immense complexity. It requires a spacecraft capable of landing, drilling, or scooping a sample, launching that sample back into space, and then returning it safely to Earth, all while contending with the object's unknown gravity field and strange acceleration. The risk of contamination, both of the sample by Earth organisms and of Earth by any hypothetical extraterrestrial material, would necessitate biosafety protocols rivaling those for the most dangerous pathogens. The political and international treaties that would need to be negotiated for such a mission are a labyrinthine challenge all their own. Despite these staggering hurdles, the global will to make this mission happen is palpable. The scientific prize is simply too great. We are not just talking about understanding another rock in space. We are potentially talking about making first contact with a non-biological intelligence, or at the very least, discovering an entirely new type of astrophysical object. The data returned could revolutionize our understanding of physics, materials science, and our place in the cosmos. Agencies are fast-tracking funding reviews, private companies are offering partnerships, and nations are jockeying for a role in what could be humanity's greatest adventure. The mission to the Monolith Comet is no longer a matter of if, but when and how. It represents our species' innate drive to reach out into the unknown, to touch the mysterious, and to finally answer a question that has captivated us since we first looked up at the stars. It is impossible to discuss this object without feeling the chilling presence of science fiction looming over the scientific data, as if we have stumbled into a narrative we thought was purely imaginative. The most immediate and powerful parallel is, of course, to Arthur C. Clarke's iconic Monolith from 2001, A Space Odyssey. In that story, a perfectly geometric black slab is discovered buried on the moon, a silent and utterly enigmatic artifact placed there by an unseen extraterrestrial intelligence to observe and catalyze the evolution of humanity. The fictional monolith is a teacher, a trigger, and a symbol of a universe filled with higher purpose. Our real-world discovery, with its stark rectangular shape and unnatural demeanor, feels like a page torn from Clarke's notebook. The resemblance is so uncanny that it forces a profound question. Did Clarke and his collaborator Stanley Kubrick somehow predict a future discovery, or have we, in our search for understanding, begun to project a beloved fictional narrative onto a natural anomaly? The comparison is thrilling because it taps into a deep-seated human hope that we are not alone and that the universe is not just a chaotic void, but contains design and perhaps even meaning. Beyond the visual echo, the object's behavior invites comparisons to another cornerstone of speculative fiction, the von Neumann probe. This concept, envisioned by mathematician John von Neumann, describes a self-replicating robotic spacecraft designed for the galactic-scale task of exploration. The premise is simple yet staggering. A single probe travels to a distant star system where it uses the raw materials of asteroids and planets to build copies of itself. Those copies then travel onward to other star systems, creating an exponential wave of discovery that could map the entire galaxy without requiring a single organic crew. The Monolith Comet, silently adrift in our asteroid belt, a literal treasure trove of construction materials, fits this profile with an almost suspicious neatness. It could be a dormant von Neumann probe, its replication systems long since deactivated or awaiting a trigger we cannot perceive. Perhaps it is not a probe at all, but a von Neumann replicator that experienced a critical error millions of years ago, leaving this single, sterile unit to wander endlessly as a ghost of a grander, unfinished plan. This idea transforms the asteroid belt from a simple junkyard of planetary formation into a potential industrial park, its resources silently coveted by a technology that arrived long before we did. The concept also brings to mind the haunting and cautionary tales of berserkers, a term popularized by author Fred Saberhagen. In these stories, the galaxy is patrolled by ancient, self-replicating machines whose sole programmed purpose is to seek out and eradicate all biological life. These are not explorers but exterminators, left over from a long-forgotten war between star-faring races. While there is absolutely no evidence to suggest the Monolith Comet is hostile, its maneuvers are subtle and non-threatening. The mere possibility that an inanimate object could harbor such a terrifying directive plays on our most primal fears. It introduces a layer of existential risk to the scientific curiosity. Should we attempt to make contact, could our investigations, however well-intentioned, be misinterpreted as a threat, activating a dormant protocol with unimaginable consequences? This fictional framework provides a valuable ethical lens through which to view our real-world actions, urging a caution that balances our desire for knowledge with a respectful acknowledgement of the unknown. Even its physical nature finds a mirror in science fiction, particularly in the realm of advanced nanotechnology and smart materials. Many stories feature utility fog or self-assembling materials that can change their shape and function on command. While our object shows no evidence of such active transformation, its hypothesized layered composition and incredible structural integrity suggest a material science far beyond our own. It brings to mind the alien debris in films like Arrival, where objects obey physical laws we have yet to discover, or the seemingly inert but ultimately transformative artifacts found in countless tales. These fictional precedents do not prove anything, but they provide a crucial cognitive toolkit. They allow us to entertain possibilities that rigid, conventional science might initially dismiss, giving us the conceptual vocabulary to even begin discussing an object that acts like a machine. In a very real way, science fiction has prepared us for this moment, providing a library of potential explanations for a phenomenon that otherwise defies categorization. It allows scientists to say, it behaves like a von Neumann probe, not as a wild claim, but as a shorthand for a complex set of characteristics that now demand serious consideration. Given the profound mystery of its composition and motion, it was only a matter of time before astronomers turned their attention outward to the space immediately surrounding the object itself. If the Monolith Comet truly possesses the density and mass of a manufactured object, or even some unknown form of internal energy, its gravitational influence on nearby space should tell a tale. Every object with mass creates a tiny dimple in the fabric of spacetime, a gravitational field that tugs on anything nearby. For a typical asteroid, this pull is so minuscule as to be virtually undetectable, lost in the far more powerful tides of the Sun and Jupiter. But for our enigmatic visitor, the question wasn't just about mass, it was about whether its gravity held any surprises of its own. The search for answers began with a painstaking analysis of the asteroid belt's local neighborhood around the comet's path. Using ultra-precise star tracking data from telescopes like Gaia, which maps the positions and motions of billions of stars with incredible accuracy, researchers looked for any subtle anomalies. The technique is ingenious. As the comet moves through the belt, its gravity, however faint, should deflect the path of any smaller, nearby objects. It should also attract and hold a cloud of fine dust and debris, a natural gravitational fender formed from the countless micro-collisions that occur in the belt. What they found, or more accurately, what they failed to find, was just as puzzling as the object itself. The first major surprise was the apparent absence of a gravitational wake. In regions of the asteroid belt where massive objects like Ceres or Vesta travel, astronomers can often detect a slight clearing or a distinctive pattern in the distribution of smaller rocks and dust, a signature of their gravitational influence over millennia. The space immediately around the Monolith Comet showed no such pattern. The density of smaller asteroids and debris along its orbital path was completely normal, statistically identical to any other random patch of the belt at that distance from the Sun. This was deeply counterintuitive. An object with enough mass and density to account for its structural integrity and strange rotation should be leaving some gravitational fingerprint on its environment, yet the evidence was conspicuously absent. It was as if the comet was massive enough to maintain its own strange cohesion, but somehow not massive enough to affect the world around it in the way we would predict. This led to the most baffling gravitational observation of all, the object's apparent lack of a dust halo. Every single asteroid and comet we have ever studied, without exception, is surrounded by a tenuous cloud of its own material. Micrometeoroid impacts constantly chip away at their surfaces, creating a faint but detectable shroud of dust that is held in a loose cloud by the object's gravity. We've seen this around tiny, kilometer-wide asteroids. Our most sensitive instruments, designed to scan for this exact phenomenon, were trained on the Monolith Comet expecting to see this classic feature. They saw nothing. The immediate vicinity of the object was pristine, almost sterilized, with no detectable dust cloud whatsoever. This is not just unusual, it is physically bizarre. It suggests one of two equally extraordinary possibilities. Either the object's surface is so unbelievably hard and resilient that it suffers virtually no micro-impacts to generate dust, a property of some advanced alloys or composite materials, or its gravitational field is so anomalously weak for its size that it cannot even hold onto the dust particles that are created, allowing them to simply float away. Both explanations defy everything we know about the mechanics of our solar system. The implications of this missing gravity signature are profound. It feeds directly back into the core mystery of what this object might be. If it is a dense, solid chunk of metal, its gravity should be noticeable. The fact that it isn't suggests that our estimates of its mass could be completely wrong. Perhaps it is not solid at all, but mostly hollow, a suggestion that immediately brings to mind the concept of a constructed vessel. A hollow object would have far less mass than a solid one of the same size, explaining the lack of gravitational pull on its surroundings, while its rigid external structure could still account for its incredible rotational stability. Alternatively, the answer might lie in a realm of physics we don't yet understand. Could the object be manipulating gravitational fields in a way that localizes its effects, containing its own gravity in a manner that prevents it from influencing the external environment? While this sounds like the stuff of theoretical physics, the utter lack of a conventional gravitational footprint forces us to consider that we may be dealing with principles of mass and energy that go far beyond Einstein's general relativity. Ultimately, the silent, unperturbed space around the Monolith Comet becomes its own kind of evidence. Its pristine void is a negative image that speaks volumes. In a region of space defined by chaotic collisions and gravitational interplay, this object travels in a bubble of eerie calm, untouched by and untouching the ancient debris that surrounds it. It doesn't behave like a gravitational body. It behaves like a ghost moving through the physical world while seemingly obeying a different set of rules. This gravitational silence is perhaps the most unsettling anomaly of all, because it strikes at the very heart of our understanding of how matter and energy are supposed to interact. It suggests that the object is not just an outlier in terms of its shape and motion, but that its very presence in our reality might be more complex and profound than we ever imagined. Over the years, as observatories around the world have meticulously tracked its journey, a vast and revealing dataset has accumulated, transforming a snapshot of strangeness into a longitudinal study of profound mystery. This long-term observation has been crucial because while a single anomaly might be a fluke, a repeating pattern of behavior over a decade is a signature. The data, compiled from thousands of individual measurements, reveals that the object's strangeness is not a one-off event but a consistent, and in some ways predictable, feature of its existence. It operates on a cycle, a rhythm that is both mechanical and deeply enigmatic. One of the most significant patterns to emerge is a clear correlation between its non-gravitational acceleration and its orbital position. The object's tiny, inexplicable bursts of speed consistently occur within a specific window of time as it reaches the perihelion of its orbit, its closest approach to the Sun. This isn't a random sputter of activity, it's a timed event like clockwork, repeating on every single orbit we've been able to observe. The acceleration profile is also remarkably consistent in its magnitude. Each perihelion kick adds roughly the same amount of delta V, the same change in velocity, with a precision that natural systems simply do not exhibit. A comet's outgassing is messy and uneven, varying in intensity based on how much ice is exposed and how it's heated. This object's propulsion, for lack of a better word, is metronomic in its reliability. It suggests a system that is not depleting a finite resource, but rather one that is harvesting energy from its environment in a highly efficient, repeatable cycle, likely using the increased solar flux at perihelion to power whatever mechanism is responsible for its movement. Beyond this annual pulse, the data has also revealed a much slower, grander trend, a gradual, intentional-sounding shift in its orbital trajectory over multiple decades. By comparing its current path to where it was predicted to be based on gravitational models from 20 years ago, astronomers have charted a deliberate, albeit tiny, course correction. It is not simply drifting, it appears to be steering ever so slightly toward a different long-term destination within the asteroid belt. This isn't a path that maximizes its exposure to the inner planets or sets it on an escape trajectory from the solar system. Instead, the calculated-in point, if this minuscule acceleration continues for another several centuries, places it into a stable orbital resonance with Jupiter, a gravitationally secure and resource-rich parking orbit that would be an ideal location for a long-term observational outpost or a base of operations. This is not conclusive proof of intent, but it is a pattern of motion that is incredibly difficult to attribute to chance or any known natural dynamic. Perhaps the most startling discovery from long-term monitoring is the complete absence of any signs of degradation. A natural object in the asteroid belt is subjected to a relentless sandblasting from micrometeoroids and cosmic radiation. Over millions of years, this weather's surfaces creates regolith and forms craters. Our high-resolution imaging over the last decade shows no new discernible impact craters on its surface. Its geometric shape remains sharp, its albedo. Its reflectivity has not diminished. It is not weathering or aging in the way that every other object in its environment demonstrably is. This phenomenal preservation suggests either a composition of incredible hardness and resilience, far beyond any known natural metal or rock, or the presence of some kind of active maintenance or repair system, a notion that strays even further into the realm of speculative technology. The long-term data doesn't just tell us what the object is doing, it also tells us what it's not doing, and its refusal to erode or change is, in its own way, just as loud a statement as its puzzling acceleration. While the mainstream search for natural explanations and the more serious consideration of von Neumann probes have dominated the scientific conversation, the sheer depth of the mystery has inevitably given rise to a spectrum of even more unconventional theories. These ideas, often residing at the very fringes of science, attempt to grapple with the object's profound otherness by invoking concepts that stretch our understanding of reality itself. One of the most enduring speculative frameworks is the ancient astronaut theory, which posits that the Monolith Comet is not a probe from a contemporary extraterrestrial civilization, but a literal artifact from a bygone cosmic era. Proponents of this view suggest it could be a relic from a pre-human, perhaps even pre-solar system, technological species. This isn't a functional machine on a mission, but rather a piece of archaeological debris, a forgotten piece of infrastructure, or a monument left behind by a civilization that rose and fell among the stars millions or even billions of years ago. Its current path through the asteroid belt might not be a carefully plotted survey route, but the final, decaying orbit of a derelict hulk, a ghost ship from a war or a diaspora so ancient that all other traces have been erased by time. This theory appeals because it sidesteps the question of why an active probe would be so seemingly inert. It doesn't need to be operational to be artificial. It simply needs to be durable, a silent stone tablet from a chapter of galactic history we never knew existed. Venturing further into the speculative, some theorists have proposed the object could be a visitor not just from another star but from another time. The concept of time travel, while a staple of fiction, is not entirely dismissed in theoretical physics, with certain solutions to Einstein's equations allowing for closed time-like curves. The idea here is that the Monolith Comet might be an artifact from humanity's own far future, sent back in time for a purpose we cannot comprehend. Perhaps it is a historical probe designed to gather baseline data about our solar system at a specific moment in its development before any significant human expansion. Maybe it is a warning beacon placed in a stable orbit to be discovered at this precise moment in our technological evolution, a message in a bottle from a future that depends on the choices we make today. Its mysterious composition and propulsion could be the product of a physics we have yet to discover, making it appear like magic to our current understanding. This theory is ultimately untestable with our current knowledge, but it captures the imagination by framing the object not as an alien other, but as a deeply human mystery from a time yet to come. Perhaps the most mind-bending category of speculation involves the possibility that the object is not entirely of our dimension. In the realm of theoretical physics and cosmology, the idea of a multiverse or higher spatial dimensions is a serious field of study. Some researchers have cautiously suggested that the comet's most baffling properties, its lack of a conventional gravitational signature, its apparent resistance to micro-impact erosion, and its non-reactive surface, could be explained if it were partially phased into dimensions beyond our own. In this model, what we perceive is merely a three-dimensional shadow or cross-section of a more complex object that exists in a higher dimensional space. Its movements might not be propelled in a way we recognize because the forces acting upon it operate in dimensions we cannot access or measure. This could explain why it seems to violate the conservation of momentum. From its full-dimensional perspective, it may not be violating any laws at all. It would be less a spaceship and more a natural feature from a parallel reality, a cosmic iceberg whose full structure and purpose are mostly hidden from our view, occasionally drifting through the manifold of space-time and briefly intersecting with our own. Other speculative ideas abound, each attempting to patch a different part of the mystery. Some propose it could be a form of cosmic-scale life, a living crystal, or a silicate-based organism whose biological processes involve the manipulation of electromagnetic fields and gravitational energy, making its movements appear technological to our limited perspective. Others wonder if it might be a localized knot of spacetime itself, a topological defect left over from the Big Bang that behaves according to its own unique set of physical rules. There are even those who play with the idea that we are living inside a simulation, and the Monolith Comet is a glitch in the code, an administrative object or a marker left by the programmers that has become visible to us. Its unnatural properties are a result of it operating on a different layer of reality than the simulated universe we perceive. What unites all these wild speculations is their shared recognition that the standard toolkit of astronomy has, so far, come up short. They represent a human desire to find a box, any box, that can contain such a profound anomaly. While these ideas lack the rigorous evidence required by mainstream science, they serve a valuable purpose. They force an expansion of the imagination. They remind us that our current understanding of the universe is provisional, and that true discovery often requires us to think in directions we previously considered impossible. The Monolith Comet, by its very existence, has become a blank canvas upon which we project our deepest questions about time, intelligence, and the ultimate nature of reality itself. Within the hallowed halls of academia and the bustling virtual corridors of international conferences, the Monolith Comet has ignited a firestorm of debate unlike any other recent astronomical discovery. This isn't a quiet disagreement over data margins. It's a fundamental schism over how to interpret a set of observations that seemingly defy categorization, forcing a very public reckoning with the limits of known science. The community has fractured into several distinct camps, each armed with their own interpretation of the data and their own philosophical stance on the burden of proof. On one side are the strict reductionists, the skeptics who argue that an extraordinary claim requires not just extraordinary but incontrovertible evidence. Led by prominent figures like Dr. Lena Markov, this group concedes the object is anomalous but insists we must be missing a piece of the natural physics puzzle. Their position is one of intellectual caution. They warn against the seductive allure of the extraordinary, pointing to a long history of mysteries, from the peculiar canals on Mars to the early theories about pulsars that were eventually explained by new but natural phenomena. For them, the null hypothesis must remain that this is a natural object, and the onus is on the proponents of exotic theories to disprove that. They focus their efforts on searching for ever more obscure natural mechanisms, suggesting perhaps a form of radiation pressure from a surface that acts like a perfect solar sail, or a novel quantum effect we don't yet understand. They argue that leaping to a conclusion of artificiality is not just premature, but a failure of scientific imagination to find a natural solution. Arrayed against them are the proponents of what might be called the anomalist position. This diverse group, which includes the original discoverers and a growing number of astrophysicists and planetary scientists, argues that the relentless failure of natural explanations is itself a form of evidence. Their mantra, echoing the famous Sherlock Holmes quote, is that once you have eliminated the impossible, whatever remains, however improbable, must be the truth. They contend that the collective evidence, the geometric shape, the alloy-like composition, the lack of dust or outgassing combined with acceleration, and the peculiar thermal signatures forms a coherent pattern that points insistently away from known geology. For them, continuing to propose increasingly contrived natural models is an exercise in ignoring the obvious. They are not claiming definitive proof of aliens, but rather arguing that the artificial hypothesis is now the simplest and most parsimonious explanation that fits all the available data, and it deserves to be funded and investigated with the same seriousness as any other leading theory. Caught in the middle are the vast majority of astronomers, the intrigued but undecided. They find the skeptics' arguments increasingly strained, yet remain uncomfortable with the profound implications of the anomalist position. This group is pushing for a different approach entirely. They argue that the debate is currently unproductive because we lack a crucial type of data. For them, the solution isn't more telescope time, but a physical mission. Their position is that only by visiting the object, by orbiting it, landing on it, and touching it, can we gather the evidence needed to break the deadlock. A single mass spectrometer reading from a sample of its surface material would instantly tell us if we're looking at a refined alloy or a bizarre new type of mineral. This centrist group is effectively acting as the bridge, translating the heated theoretical debate into the practical, mission-driven planning that now dominates agency discussions. The tension between these factions has spilled over into some of the most electrifying conference sessions in recent memory. At the latest International Astronomical Union Symposium, a dedicated session on the object had to be moved to the largest auditorium after overwhelming demand. The question and answer period following the presentations was not the usual polite exchange of technical details. It was a charged, sometimes tense, series of challenges and defenses. One senior researcher was openly heckled after presenting a complex new model for nitrogen ice sublimation that critics immediately pounced on for its thermodynamic impossibilities. Another presenter arguing for the artificial hypothesis was met with a barrage of sharp, skeptical questions about signal contamination in the radio data, leading to a spirited and public disagreement over statistical methodologies. These aren't personal fights, they are the sound of science struggling with something new, the necessary and healthy friction that occurs when a paradigm is challenged. The very existence of this debate happening at the highest levels of mainstream astronomy is a testament to the object's power to force us to look up and wonder, not just about what's out there, but about how we, as a species, go about asking the biggest questions of all. News of the discovery did not stay confined to academic journals for long. A low-key press release from the Pan-STARRS team, intended to share an intriguing anomaly with fellow astronomers, was picked up by a tech blogger who aptly titled their post, "Have we found a monolith?" The phrase, loaded with cultural significance, went viral overnight. The public response was immediate and electric, a global wave of fascination that crashed over the usual backdrop of daily news. This wasn't just another space rock, it was a mystery that seemed to speak directly to our deepest hopes and fears about the cosmos. Social media platforms became a battleground of ideas, with hashtags like Monolith Comet and Space Machine trending worldwide. Armchair astronomers shared enhanced images, science fiction fans drew parallels to their favorite stories, and conspiracy theorists wove elaborate narratives, all feeding a collective hunger for answers. The object's blend of scientific credibility and sheer strangeness made it the perfect catalyst for global engagement, uniting people across languages and cultures in a shared moment of cosmic wonder. The media machine, sensing a story with limitless potential, descended with full force. Outlets quickly split into two distinct camps, creating a stark divide in how the public consumed the information. On one side were the serious scientific journalists and reputable organizations like Nature, Science News, and the BBC's Science Desk. Their reporting was careful, measured, and full of necessary caveats. They led with phrases like puzzling anomaly and unexplained acceleration, meticulously explaining the Yarkovsky effect and the challenges of spectroscopic analysis. They quoted Dr. Petrova and Dr. Thorne at length, providing crucial context about the long process of scientific discovery and the importance of ruling out natural causes. This responsible reporting was a vital anchor, ensuring the public had access to the actual facts amidst the growing storm of speculation. On the other side was the sensationalist press, which unleashed a torrent of headlines designed for maximum clicks. Tabloids and certain online portals ran with covers screaming, "Alien probe found in asteroid belt," and "NASA silent on space machine discovery." These stories often cherry-picked the most exotic scientific details while ignoring all the cautious disclaimers, blurring the line between hypothesis and confirmation. Talking heads on cable news debates shouted over each other, with one side passionately arguing for the artificial hypothesis, while the other dismissively labeled it all a case of instrument error or wishful thinking. This created a confusing dichotomy for the average person. Were scientists on the verge of announcing first contact, or was this all a big misunderstanding? The complex, nuanced truth was lost in the simplified, polarized narrative, leaving many to choose which version of reality they preferred to believe. This media frenzy inevitably bled into popular culture, transforming the Monolith Comet from a scientific subject into a full-blown cultural phenomenon. Late-night talk show hosts crafted monologues about our new celestial neighbor, joking about its intentions and what we should say to it. A popular streaming service almost immediately announced a high-budget documentary series, The Silent Guest, featuring dramatic reenactments and interviews with both scientists and science fiction authors. The music world responded too. An ambient music artist released a critically acclaimed album titled PSTSJ07. Its tracks built from sonified data of the object's light curves and radio emissions. Perhaps most tellingly, the comet became a ubiquitous visual motif. Its distinctive slab-like shape appeared in advertisement campaigns for everything from new smartphones to car insurance, a shorthand for cutting-edge technology and mysterious allure. It was no longer just an object in space. It had become a mirror for our own technological aspirations and ancient anxieties. The discovery also sparked a fascinating and at times fraught philosophical and existential dialogue. Beyond the question of what is it, people began asking a deeper question. What would it mean? Theologians and philosophers debated on panels about the implications for human identity and religion. Would finding a non-living, machine-like artifact be just as profound as discovering biological aliens? Ethicists began publishing papers on the potential protocols for interacting with such an object, pondering the risks and moral responsibilities. Was it a piece of property, an archaeological site, or a sovereign entity? This public grappling with the bigger picture showed a mature, collective attempt to place ourselves within a larger cosmic context. The Monolith Comet, by its very existence, had become a catalyst for a global conversation about humanity's place in the universe, challenging us to grow up as a species and think beyond our planetary cradle. In response to both the public thirst for knowledge and the media's tendency toward distortion, the scientific community undertook an unprecedented effort at public outreach. The astronomers behind the discovery, like Dr. Petrova and Dr. Thorne, found themselves not just researchers but also diplomats and educators. They participated in countless Reddit essays, YouTube explainers, and citizen science webinars, patiently answering questions and demystifying the process. The iCare Consortium launched a sleek, accessible website that provided raw data, visualizations, and regular updates in plain language, aiming to crowdsource analysis and keep the public accurately informed. This transparent approach helped build a bridge between the complex world of academic research and the curious global audience, fostering a sense of shared investment in the mystery. The world wasn't just a passive spectator. Through these efforts, it became a participant in the greatest detective story ever told, with a silent, tumbling slab of metal as its central clue. With the world's attention now firmly fixed on this celestial enigma, the scientific community is mobilizing with a level of international cooperation rarely seen outside of crisis response. This isn't about casually adding a few more hours of telescope time. It's a fundamental reprioritization of resources, a global effort to design and deploy a new generation of tools specifically tailored to unravel this one specific mystery. The overarching strategy is a multi-pronged assault, combining relentless observation from Earth with the bold and necessary goal of finally sending a probe to meet this object face to face. On the ground, the world's most powerful observatories have effectively been put on a wartime footing for astronomy. The James Webb Space Telescope has had entire cycles of its observing schedule reallocated, its unparalleled infrared gaze focused on performing a deep molecular biopsy of the object's surface. Its mission is to hunt for the spectral signatures of individual isotopes within the suspected alloys, ratios that could definitively prove a non-natural origin. For instance, the ratio of iron-60 to other isotopes could indicate whether the metal was forged in a supernova or, alternatively, in a controlled industrial process. Simultaneously, the Hubble Space Telescope is engaged in a long-term photometric campaign, taking ultra-high-resolution images every time the object's rotation brings a new face into view, slowly building a pixel-by-pixel map of its entire surface to search for the tiniest of features, seams, ports, or even symbols. New Time on the Very Large Array in New Mexico has been exclusively dedicated to a new type of radar analysis. Instead of just listening for signals, scientists will be actively pinging the object with powerful radar waves, not as a message but as a diagnostic tool. By analyzing the precise way those waves bounce back, they can create a detailed three-dimensional map of its internal structure, searching for hollow chambers, varying densities, or internal geometries that would be the smoking gun for a constructed object. But the real innovation is happening in the labs and engineering firms where new instruments are being conceived from the ground up. The unique challenges posed by the Monolith Comet have become a catalyst for technological leaps. A consortium of European universities is fast-tracking the development of a hypersensitive quantum magnetometer, small enough to be deployed on a future spacecraft but powerful enough to detect the faintest, most localized magnetic fields. The goal is to distinguish between the broad, planetary-scale magnetic field of a natural iron-nickel core and the sharp, fluctuating fields that might be generated by active, internal electrical systems. In Japan, researchers are pioneering a new form of long baseline interferometry, linking radio telescopes across the entire hemisphere to create a virtual telescope dish the size of the Earth itself. This colossal resolving power could, in theory, allow them to image the object's surface in stunning detail from right here at home, potentially spotting features as small as a dinner plate, and finally putting to rest the debate over its true texture and geometry. This unprecedented effort is being coordinated by the International Cometary Anomaly Research Effort, or ICARE, which has evolved into a true mission control for the global investigation. ICARE's role is to act as a central nervous system, ensuring that every observation is complementary. When the James Webb Telescope identifies a specific region of interest with an unusual thermal signature, it immediately alerts the radar teams at the Very Large Array to focus their pings on that exact spot, while notifying the optical telescopes to watch for any visual changes. This seamless, real-time collaboration prevents duplication and ensures that the object is being studied in a holistic way, with each data point layering onto the last to build a complete picture. Private entities sensing both the historical significance and potential commercial applications of any discovered technology are also clamoring to contribute. SpaceX has publicly offered a dedicated, cost-price Falcon Heavy launch for any approved mission, while several venture capital firms have established substantial grants for research into advanced propulsion and material science inspired by the object's baffling properties. Yet, everyone involved understands that these Earth-based observations, as advanced as they are, can only take us so far. They can tell us what the object is made of and how it moves, but they cannot tell us what it is. The ultimate goal, the undeniable focus of all this furious activity, is to get there. The mission concepts that were once speculative blueprints are now in active, funded development. NASA Aram flyby mission is being designed for a rapid launch, a high-speed interstellar bullet that will sacrifice long-term study for the chance to get a single, breathtakingly close look. Its camera system is being engineered to resolve features down to the millimeter, hoping to finally see if that geometrically perfect surface is etched with the microscopic scars of space weathering or is as flawless as it appears from a distance. The European Space Agency's more ambitious Cori Rendezvous mission represents the full investment in this mystery. Its design includes not just an orbiter, but a separate, hardened impactor probe. The plan is to deliberately crash this impactor into the surface at a calculated angle, and then have the main orbiter fly through the resulting ejector cloud, analyzing the composition of freshly exposed internal material, a cosmic version of cracking open a geode to see what's inside. The data from even a failed mission would be invaluable, but the hope, the quiet driving force behind this global endeavor, is that one of these spacecraft will finally close the distance and send back an image so clear, so undeniable, that it will answer the question once and for all, transforming human history in a single, silent transmission from the depths of the asteroid belt. The implications of this object for our entire field of astronomy cannot be overstated. We are facing a potential paradigm shift, a moment where the foundational assumptions we've used to map the solar system for centuries are being called into question. For so long, our models have been built on a framework of predictable natural forces, gravity, collisions, and thermodynamics shaping inert rock and ice over billions of years. The Monolith Comet doesn't just bend these rules, it operates as if they are mere suggestions. Its very existence introduces a new variable into the cosmic equation, one for which we have no established constant, the possibility of directed, non-biological agency. This forces us to consider that our solar system might not be the quiet, natural wilderness we presumed, but something more complex, a landscape that could contain both ancient ruins and active machinery, all hiding in plain sight within the asteroid belt's chaotic dance. This discovery fundamentally challenges the principle of uniformity, a cornerstone of modern science which assumes that the physical processes we observe today have operated consistently throughout the history of the universe. We look at other star systems and make assumptions about planet formation based on our own. We study asteroids and comets as pristine relics of that process. But if even one object in our own backyard defies this natural history, it forces a profound reassessment. How many other anomalies have we dismissed as instrument error or statistical outliers? How many strange light curves or odd orbits have been quietly filed away because they didn't fit the established model? The Monolith Comet acts as a key, unlocking a new way of seeing. It encourages a form of scientific skepticism that is not cynical, but brilliantly open-minded, where the next great discovery might not be a confirmation of our theories, but a glorious exception that shatters them. The potential scientific revolutions it could trigger extend far beyond astronomy, rippling into physics, materials science, and even philosophy. Imagine confirming that its composition is indeed a perfected, ancient alloy. The study of this material alone would launch a new era of metallurgy and engineering, offering insights into durability and strength that could transform everything from spacecraft design to everyday technology. Its method of silent propulsion, if we could ever understand it, would represent a breakthrough in physics, potentially harnessing fundamental forces in ways we have not yet dreamed of, rendering our chemical and ion rockets as primitive as steam engines. This isn't just about finding a new object, it's about potentially discovering an entire new branch of applied knowledge, a library of advanced technology left drifting in orbit for us to find. On a deeper, more philosophical level, the object forces a re-evaluation of our place in the cosmos. The Copernican principle taught us we are not the center of the universe. The discovery of exoplanets showed us we are not unique in having a home. But the Monolith Comet suggests something even more humbling and awe-inspiring. We may not be the first, the only, or even the most advanced intelligence to call this solar system home, even if that intelligence was artificial. It introduces the staggering concept of deep time, not just for geology and biology, but for technology itself. It raises the possibility that technological civilizations could rise and fall on timescales so vast that their artifacts simply outlast them, becoming permanent, silent features of the galactic landscape, waiting for the next curious species to stumble upon them and wonder. This shifts the search for extraterrestrial intelligence from a quest for signals to a form of cosmic archaeology, where the evidence of others might not be a message but a monument. So as we stand on the precipice of discovery, looking back at the mountain of evidence, a clear and startling picture emerges. This is not a collection of isolated oddities, but a cohesive pattern of behavior that points relentlessly away from the natural world. We have an object with a stark, geometric form unlike any asteroid or comet. We have a surface of polished, alloy-like material that shows no signs of weathering after eons in space. Most damningly, we have consistent, non-gravitational acceleration with no detectable exhaust, no outgassing, no natural propulsive mechanism whatsoever. It steers, it corrects its course with a precision that mimics a spacecraft's perihelion kick. It maintains a stable rotation and a strangely managed thermal profile, all while sitting in a gravitational silence, failing to attract the dust cloud that should surround it. Every single natural explanation, when subjected to the cold, hard light of physics, has crumbled. The only hypothesis that accommodates every one of these bizarre characteristics is the one that suggests we are not looking at a natural formation, but at a piece of technology. A machine. What does this mean for us, for our place in the cosmos? If this interpretation holds, it would be the most profound discovery in human history, fundamentally rewriting our understanding of life, intelligence, and time itself. It suggests that our solar system is not a pristine wilderness, but a place that has been visited, and perhaps even inhabited, by a non-biological intelligence that could be millions of years older than our entire species. We would have to confront the humbling reality that we are not the first, the only, or even the most advanced actors on this celestial stage. The universe may be not just full of life, but also littered with the enduring artifacts of civilizations that rose and fell in the deep, dark gulfs of time long before Earth even cooled. This object could be a monument, a probe, or a solitary tombstone, a silent witness to a story so vast we can scarcely imagine its chapters. And so we are left with one final, haunting question, a question that now drives billions of dollars in mission planning and occupies the minds of the world's greatest scientists. As you look up at the night sky, knowing this strange, silent slab is tumbling through the endless dark, are we witnessing the limits of our own understanding? A spectacular natural phenomenon we simply haven't learned to explain yet, or are we, for the very first time, staring at the undeniable signature of something truly, authentically, and